Greetings everyone, my name is Gabriel Polietsky and I am an undergraduate student from Polo Labs and I will presenting for you today the article entitled A First Principle Model for Axial Fans Optimization Results of Blade Pitch Angle, which was carried out with the advertisement of the Professor Marcelo de Oliveira, Engineer Adriano Roloni and Professor Christian Adams. So without any further ado, the object of study in this work are low pressure axial fans. They are used in condensing and evaporating units of refrigeration systems. Therefore, improving the fan designs allows for more energy efficiency. The current state of the art in axial fan design is based on a trial and error process using experimental and numerical tools like wind tunnels and CFD. The approach put forward in this work relies on a first principle model that allows for fast sensitive analysis and extensive optimizations. The model considers a discretized blade along the radial direction, and the elements are solved one by one with a formulation based on the tripod formed by the airfoil aerodynamics that describes the aerodynamic forces on the blade section, the blade element theory that translates the aerodynamic force into the axial and tangential coordinate system, giving rise to the thrust and torque components, and the conservation of momentum that describes the effect of the blade force on the flow. These model pillars will be briefly discussed in the sequel. The airfoil aerodynamics is described by the open source software Xfoil that evaluates the lift and drag coefficients for a certain profile given the Reynolds number and the angle of attack. To run the Xfoil, it is necessary to make a translation of the available fan CAD. First, the profile for a given radius is rotated and mirrored for an appropriate position of the Xfoil. Then a point cloud is generated along the profile boundaries. The Xfoil generates the maps, but not all the points can be solved. Therefore, an interpolation to fill in the blanks is made. These maps will be later used in the model. The blade element theory consists basically on the description of the drag and lift forces in the coordinates of interest, yielding the thrust force that propels the flow and the torque necessary to maintain the blade movement. In the figure it can be seen the pitch angle represented by the letter theta, the resultant velocity over the blade formed by the axial and tangential velocity components, and the angle of attack of the resultant velocity. The equations 1 and 2 on the left side of the figure are derived by trigonometric relations as well as the equations 7 and 8 that define the thrust and the torque. These equations are used to solve the model. The momentum conservation describes the effects of the axial and tangential forces over the flow. The axial derivation is made for a streamline based on the Bernoulli principle and considers the case of a fan tested in a wind tunnel. For this setup, the pressure difference over the fan is the difference of static pressure measured by a transducer, represented by this delta PE symbol, plus the drop of static pressure caused by the airflow acceleration at the fan intake. The latter pressure share is later recovered at the fan exhaustion to the atmosphere, where the static pressure equals zero. The tangential derivation couples the tangential forces of the blade with the airflow through and accounts only for acceleration effects. It basically equals the tangential force with the variation of the tangential momentum of the flow. The complete derivation is shown by Halter and Karpner. The equations are shown below the figure and are used to solve the model. The model assumption is that there is no radial flow. In other words, there is no airflow between the elements. This implies on a radial pressure field that is associated with the flow through. The difference of static pressure between neighboring elements is given by the equation below the figure and derives from the Navier-Stokes equation for the conservation of momentum in the radial direction in cylindrical coordinates. In the figure it can be seen a scheme of the downstream pressure field that, once integrated, must return a zero mean of static pressure, since the fan exhausts to the atmosphere. Also in the same graph, it can observe that the pressure increases with the radius. This pressure gradient is responsible for the centripetal force that keeps the airflow from moving outwards in the radial direction. For a greater physical constant, it was chosen a staggered grid for the flow and pressure meshes. Once the airflow through evaluated on the blade element depends on the pressure at its boundaries. The table shows the inputs of the model as well as their values for the analyzed fan in this work. The inputs are mostly of geometric nature, being the hub and the blade radius, the number of the blades, the chord length, and the pitch angle, both of which can be varied along the radius. The lift and drag coefficients that are given by the X-foil lookup table and are dependent of the blade profile that can be varied along the radius too. The non-geometric parameters are the rotor angular speed, the air density and the air kinematic viscosity, which are both dependent on the air temperature, and the global static pressure difference that is varied so that the fan characteristic curve can be generated. The nonlinear system resultant of the equations already shown is solved by a method of substitution with under-relaxation. Initially, a uniform pressure distribution is assumed. The algorithm starts solving the most external element since their solution is more easily obtained. The model follows the element loop where the equations shown before as well as the X-foil maps are evaluated until convergence is achieved. The process is repeated until all the elements are solved or an element is found to be unsolvable. Then the pressure distribution is corrected to respect the global difference pressure imposed in the wind tunnel. The solution algorithm is finished when the variation of the variable distribution is smaller than the tolerance. Once the model converges, an integration of the outputs of the elements is made to determine the fan outputs, mainly the power consumption and the airflow. In the inner elements of the model, a phenomenon of insolvence takes place, where no mathematical solution for the nonlinear system can be found. It occurs because with the reduction of the radius there is a reduction of the chord length. To compensate for that, a larger lift coefficient is required to maintain the thrust, which is in turn demand a higher angle of attack until the stall point is reached. From there on, further increasing the angle of attack leads to an abrupt reduction of the lift coefficients, giving rise to the element insolvence. The flow and the torque of the insoluble elements are simply disregarded when computing the global outputs. Because of that, an extrapolation method was developed to determine how the characteristic curve would look like if all the elements could be solved. To that end, it is assumed a linear distribution of axial velocity, as shown in the figure. With this assumption, it is possible to estimate the overall airflow based on the airflow of the solved elements and the radius where the insolvence first is observed. The process used for the power correction is analogous, but considers a quadratic variation. In the figure, it is shown the head and the power consumption curves as a function of the volumetric airflow. It can be seen that for low head values, the model can predict the airflow and the power consumption with an overestimation of 10 and 20% respectively. This is attributed to unmodeled non-idealities, such as the flow disturbance between blades and the blade tip losses. As the head grows, the model still predicts well the actual fan behavior. However, for head values above 10 Pascal, the prediction detaches from the experimental trends. The correct model indicates that if all the elements could be solved, the actual curve trends could be predicted even for higher head values, which indicates that the current model is promising. Based on these results, the authors concluded that the model as is could already be used for an optimal blade design exercise. The pitch angle is a parameter with a strong impact on the fan performance, and it is easy to be implemented in a manufacturing process. Therefore, it was chosen as the first parameter to be optimized in a design exercise. The objective of the optimization is to be as wide as possible, not suffer from any initial bias, whereas testing the capability of the model and allowing for new design insights. To this end, a very large number of pitch angle combinations had to be tested, which could only be simulated to the very low computational cost of the developed model in comparison to CFD techniques, for instance. Despite the low computational cost, a specific discrete optimization strategy had to be devised given the combinatorial nature of the problem, once this is essentially a multivariable optimization. The optimization process starts with only a 4-element discretization considering 17 levels of pit angle between 10 and 50 degrees, which is the range commonly observed in commercial fans. The combination of all the possibilities gives a total number of 83,521 simulations. The optimal distribution of 4 elements is then interpolated to a 5-element distribution, and the process is repeated, now varying the possible values from the optimal distribution already calculated. The algorithm follows this refinement process with 5 elements 2 more times, each time with a lower step size. The refinement proceeds to a 6, 7, and 8 element discretization, when the distribution is considered refined enough. To allow for such a large number of simulations to be executed in the shortest time possible, lookup tables of the elements were previously created that describes the element's output as a function of the angle of attack, the radius, and the pressure difference. With these pre-computed maps, there is no need to repeatedly solve the elements during the optimization routine, which dramatically decreases the optimization time. With this strategy, about 800,000 simulations could be performed in less than 1 hour. The video shows the simulation process through several refinement steps. The points simulated in the process are represented in the video as a function of the power consumption and the volumetric airflow. In the graph, it can be seen a well-defined Pareto front that determines optimal fan configurations. The black dot indicates the baseline fan performance. It can be noticed that the black dot is not at the boundary of the Pareto front, indicating the existence of solutions for which either more flow can be obtained with the same power consumption or less power can be spent to obtain the same flow. In the process, the chosen optimal distribution was the one with the lowest consumption among those with at least the baseline case flow. The optimization process was carried over for head values of 0 and 10 Pascal. In the graph, it can be noticed that the optimization distribution tends to have a decrease in the pitch angle with the increase of the radius. It was found that this configuration leads to a smoother axial velocity field, with the advantage of wielding the same airflow at the expense of less shaft power. A comparison between the baseline and the optimized CAD drawings can be seen in the right side of the graph. In the upper line, the graphs show the numerical results, that is, the simulations. In the left-hand side graph, it can be seen that both the optimized distribution have a good agreement with the baseline case for a head curve. For the power curve, one can note that the optimization leads to distributions with less power consumption, as expected. As a consequence of the lower consumption in the same flow, the optimal fans have a higher efficiency over the entire curve. The experimental results shown in the lower line confirm the tendency of practically maintain the same flow with a lower consumption for low head values. But the consumption, although lower for the entire curve, is not as low as expected, so that's no clear distinction of efficiency could be detected from the baseline fan. This is attributed to a still incipient process of CAD drawing and 3D printer manufacturing. The main conclusions of the work are: based on physical relations, a tailor-made model capable of evaluating a fan curve was developed for low head values, with an overestimation of fan head and power consumption of 10 and 20% respectively. An extrapolation strategy was used for the yet unsolved inner blade elements, yielding consistent results. Through a wide range of simulations, a blade with an optimized pitch angle distribution was designed, which, according to the model, maintains flow and reduces consumption by about 10% in comparison to a baseline fan. The optimized blade was prototyped through 3D printing, but a clear consumption reduction could not be observed, probably due to the yet incipient CAD and manufacturing process. Future work includes improving the model with non-idealities such as blade tip recirculation and momentum transfer between elements, revisiting the zero radial flow assumption, and optimizing other fan parameters. I thank you for your attention and would gladly take some questions now.